Now, let's see low temperature refrigerators. We can achieve lowest temperature of material using cryogenic liquid at 4.2 Kelvin, which is boiling point of liquid helium at 1 atm. To lower material's temperature down to 4.2 Kelvin, we simply place it in a jar filled with liquid helium. However, some cooling processes are required to get the temperature of the substance below 4.2 Kelvin. Several methods for lowering the temperature below 4.2 Kelvin have been developed. The most extensively utilized cooling techniques are divided into two categories: evaporation and demargination cooling. The helium-3 evaporator, the helium-4 evaporator, and helium-3, helium-4 dilution refrigerator are three different types of evaporation processes. The electronic and nuclear demargination refrigerators, on the other hand, are two types of demargination cooling. Each refrigerator has a minimum temperature that it can reach, which is determined by the physical properties of the refrigerator system. The lowest temperatures attained with the evaporator are 1 Kelvin, 0.3 Kelvin, and a few millikelvin for the helium-3 evaporator, helium-4 evaporator, and helium-3, helium-4 dilution refrigerator, respectively. On the other hand, electronic and nuclear demargination cooling methods yield lowest temperatures of a few millikelvin and microkelvin, respectively. Now let's first see the helium evaporators. The temperature is lowered below 4.2 Kelvin using the helium-3 and helium-4 evaporators. Pumping evaporates the liquid helium in these evaporators. The heat absorbed by forcibly evaporated helium atoms via pumping absorbs heat from their surroundings, lowering the temperature of liquid helium. This is the same cooling effect we get when we use a fan on a hot summer day. We feel chilly because the water molecules on our skin evaporate by absorbing the heat from our bodies. The evaporation of water on the skin is accelerated by using a fan. So fan corresponds to the pump in the helium evaporators. The helium atoms, helium-3 and helium-4, are the two types of stable helium. In comparison to a helium-3 atom, helium-4 atom possesses one more neutrons in its nucleus. As a result, liquid helium-3 is more prone to evaporation than helium-4. Thus, helium-3 evaporator's lowest possible temperature is lower than the helium-4 evaporators. The lowest temperature a helium-4 evaporator can get is around 1 Kelvin. A helium-3 evaporator, on the other hand, can achieve roughly 0.3 Kelvin. Helium atoms make up around 0.0013% of the air. The percentage of helium-3 atoms in these atoms is only 10 to the minus 5%. As a result, pure helium-3 gas can only be obtained through a series of sophisticated operations, making it extremely expensive. Now see the cooling power of evaporator. Controlling the vapor pressure of liquid helium-4 or helium-3 in the evaporator, which is done by pumping gas above the liquid, resulting in cooling. The evaporating gases give the cooling power by absorbing the surrounding heat energy, latent heat, needed for evaporation. Thus, the cooling power is expressed as this equation. Here, L is the latent heat and N dot is the molar rate of gas evaporating per unit time. According to Clausius-Clapeyron relation, the vapor pressure as a function of temperature is given as this equation. If we assume LT is constant, then the solution to the above equation is given by this relationship. As temperature decreases, the pumping rate, the cooling power, decreases logarithmically, since the amount of gas to be pumped out is proportional to vapor pressure. So as temperature decreases, temperature T is here, so vapor pressure decreases logarithmically, so the gas to be pumped out is very small, so pumping rate decreases very fast. Figure below depicts the schematic of helium-4 evaporator. This one. The helium-4 part is the most significant component of this refrigerator. The vacuum pump is connected into the pot. So vacuum pump is connected to this helium-4 pot. As a result, the liquid helium inside the pot is evaporated by the pump. The pot will run dry when the liquid helium in it evaporates. For continuous cooling, liquid helium must be supplied to the pot. This is done by the use of the impedance that connects the pot and the door. So outside door, helium reservoir is still here, and as function due to the function of the impedance, the helium from reservoir is put into the helium-4 pot. Liquid helium should be supplied appropriately during the cooling process. Liquid helium rises up the vacuum tube if too much liquid helium is supplied to the pot. Then the level of this liquid helium in the pot increases if the too much liquid helium is supplied. If there isn't enough liquid helium, the pot will dry up and the cooling process will come to a halt. So liquid helium should be supplied appropriately during the cooling process to the pot. An impedance is made by inserting an extended stainless steel wire into a copper-nickel capillary. The wire and the capillary have the same outer diameters. As a result, in order to insert the wire into the capillary with the same diameter, we must extend the wire to make the wire's diameter slightly smaller than the capillaries. Liquid helium flows into the pot through the small space between the wire and the capillary. Actually, the flow rate of liquid helium into the pot is determined by this space. The appropriate flow rate of liquid helium into the pot is determined by the size of the pumping tube and vacuum pump's pumping rate. As a result, we must construct an appropriate impedance in light of these conditions. Tile nature of liquid helium-3 is greater than that of liquid helium-4. We can get a temperature lower than 1 Kelvin by evaporating liquid helium-3 instead of using liquid helium-4 evaporator. A helium-3 evaporator is depicted schematically in the figure. There is a helium-3 pot in addition to helium-4 pot in the helium-3 evaporator. So we have helium-4 pot and we have also helium-3 pot. The helium-3 gas is liquefied by passing it through the helium-4 pot at 1 Kelvin, and the liquid accumulates in the helium-3 pot. So helium-3 gas is supplied, and this gas passes through the helium-4 pot as 1 Kelvin. The helium-3 will become liquid and accumulates in the helium-4 pot. The vacuum pump then evaporates the liquid helium-3, lowering the temperature of the helium-3 pot. So pump is connected to the helium-3 pot, and this helium-3 gas will be pumped out by this vacuum pump. Then the temperature of this helium-3 pot will be lowered. The evaporated helium-3 gas should not be pumped into the atmosphere since it is too expensive. As a result, we must return it to the helium-3 pot. So through the leak detector, the helium-3 gas is pumped out, and this gas will not go to the atmosphere. Instead, passes through the leak detector and put again into the helium-3 pot. So we must return it to the helium-3 pot. To check for any leaks in the pipe, helium-3 gas is fed via leak detector. So leak detector is here. The temperature of the helium-3 pot remains around 0.3 Kelvin due to the continuous recycling of the helium-3 atom through the tubes connecting the helium-3 pot. So continue to supply the helium-3 through this line. So continuous recycling of helium-3 atoms through the tubes connecting a helium-3 pot, vacuum pump, and leak detector. So evaporated helium-3 gas passes through the leak detector and then fed into the helium-3 part again. So passing through the helium-4 part, this gas will become liquid and put into the helium-3 part. Now let's see the helium-3, helium-4 dilution refrigerator. London proposed in 1951 that the temperature could be decreased even more by evaporating a mixed liquid of helium-3 and helium-4. The so-called dilution refrigeration technique did not work until 1956, when phase separation in the mixed liquids was discovered. At temperature below 0.83 Kelvin, the mixed liquid is separated into two liquids. The helium-3 liquid flows above the helium-4 liquid, since this helium-4 liquid is slightly heavier than the helium-3 liquid. So helium-3 liquid flows above the liquid-4 rich liquid, because helium-4 liquid is slightly heavier than helium-3 liquid. At temperatures below 0.83 Kelvin, the phase boundary becomes apparent, and this phase boundary and phase separation occurs. Above the phase boundary, the liquid helium-3 is 100% below 0.2 Kelvin. So pure helium-3 liquid is located above the dilute liquid. The liquid above the phase boundary is called helium-3 concentrated liquid. The helium-4 rich liquid, the dilute liquid, below the phase boundary, on the other hand, contains a small amount of helium-3. So in this dilute liquid, several percent of liquid helium-3 contained in liquid helium-4. The dilute liquid is the liquid below the phase boundary. Okay, so Walters and Fairbanks discovered phase separation in 1956. Dilution refrigeration became available as a result. Pure helium-3 liquid flows above the helium-3 and helium-4 mixed liquid when phase separation occurs below 0.83 Kelvin. Even at absolute zero, 6.3% of helium-3 can be contained within the mixture in this dilute liquid. At the temperature of 2.17 Kelvin, the pure helium-4 liquid becomes a superfluid at atmospheric pressure. At this point, 2.17 Kelvin. This temperature is referred to as the lambda point. A superfluid is a state of liquid that has no viscosity. There is no electrical resistance to the flow of electric current and the superconductivity. As a result, superfluidity and the superconductivity are quite similar. The lambda point for pure helium-4 liquid is 2.17 Kelvin as shown in the phase diagram. So pure helium-4, so there is no helium-3, so at this point. So x-axis represent the concentration of the helium-3. So 0 means there is no liquid helium in the mixed liquid, so dilute liquid. So at that point, the supertransition temperature is to 0.17 Kelvin at this point. If liquid helium-3 is mixed with liquid helium-4, however, the lambda point changes. Okay? So if we put the more liquid helium-3 in the dilute liquid, then lambda point is changing, right? This way. The lambda point decreases as the concentration of liquid helium-3 increases, following the lambda point in the figure, also following the lambda line. This lambda line. So as the concentration of liquid helium-3 increases, the supertransition temperature is decreasing in this way, following the lambda line. The phase separation occurs when the temperature is decreased below 0.83 Kelvin, the triple point. So at this point, so at this temperature is 0.83 Kelvin here. The concentration of liquid helium-3 in the concentrated liquid on the top layer increases as the temperature decreases, following the coexistence line C to C prime to approach 100% at the temperature below around 0.2 Kelvin. So a concentrated liquid, the helium-3 content will become 100% around 0.2 Kelvin. Okay. So concentration of helium-3 increases, then is follow this line, and at this temperature 0.2 Kelvin, in the concentrated liquid, helium-3 content will become 100%. The concentration of liquid helium-3 in the dilute liquid, on the other hand, decreases as the temperature decreases, following the coexistence line, dd prime. So this line. So concentrated liquid follow this C prime line, but the dilute liquid follow the D prime line. Okay. So at absolute zero, the content of helium-3 will be 6.3%. So at 0, 6.3% helium-3 content. This means that even at absolute zero, the dilute liquid at the bottom layer can contain 6.3% liquid helium-3. Okay. So this phase diagram of mixed liquid helium-3 and liquid helium-4. Dilution refrigeration uses the same cooling method as the helium-3 or helium-4 evaporator. The helium-3 atoms in the concentrated liquid on the top evaporate into the dilute liquid on the bottom if the bottom of the mixed liquid is pumped at the temperature below 0.83 Kelvin. The nearly liquid helium-4 makes up the dilute liquid. At this temperature, 8.3 Kelvin, less than 0.83 Kelvin. At this temperature, the liquid helium-4 is a superfluid and so behaves like a vacuum. As a result, evaporating helium-3 atoms into a dilute liquid is essentially the same as evaporating helium atoms into vacuum in a helium-3 or helium-4 evaporator. So basic principle of dilution refrigeration is the same as that of the helium-3 or helium-4 evaporator. The temperature of the mixed liquid is decreased as the evaporating helium-3 atoms absorb heat from their surroundings. Even at absolute zero, 6.3% of helium-3 atoms can exist in the mixed liquid, as previously stated. The cooling process is achievable even at absolute zero because of mixed liquid's characteristics. If the helium-3 atoms cannot be mixed into the dilute liquid at absolute zero, the evaporation into the dilute liquid will be impossible and we will be unable to continue our cooling process toward absolute zero. Fortunately, even at absolute zero, the helium-3 atoms can be contained in the dilute liquid, allowing the dilution refrigeration method to achieve a temperature near absolute zero. The dilution refrigeration technique can actually achieve a low temperature of around 0.002 Kelvin, so 2 millikelvin. Now let's see why at even absolute zero can 6% of helium-3 atom be mixed up with the helium-3 helium-4 mixture. The helium-3 concentrated pure liquid is floating above the diluted helium-3 helium-4 liquid when the phase separation takes place. The chemical potential of helium-3 in both liquids should be the same when two liquids are in equilibrium. The change in energy that occurs when a particle is added is referred to as chemical potential. As a result, the latent heat, which is the heat energy that evaporated helium-3 atom from its surroundings, observes as the same magnitude but opposite sign as the chemical potential of the 3 helium-3 atom in the concentrated liquid per mole, mu 3C. So as a result, this relationship, chemical potential of helium-3 atom in the concentrated liquid is the same as the negative of the latent heat. Okay. The energy required for the helium-3 atom in the concentrated liquid to break its bond with the liquid is also referred to as a latent heat. As a result, the helium-3 atom's binding energy in the concentrated liquid is related to the latent heat. So, these facts lead us to the conclusion that this equation here and A is the Avogadro number. Okay. So chemical potential is the same as the negative of the latent heat. So this relation holds. And also the latent heat is the same as the binding energy. So we can get this relationship. Let's now think about the helium-3 atoms chemical potential in the dilute liquid. Right? The binding energy of the helium-3 atoms is given as this equation. Here, helium-3 atom is mixed into a dilute liquid that contains no helium-3 liquid. That is, when the helium-3 atoms is mixed into the pure helium-4 liquid, where 0 denotes that there is initially no helium-3 atoms in the diluted liquid. So the chemical potential of the liquid of helium-3 in the diluted liquid is related to the chemical potential of helium-3 atom in diluted liquid at the moment that there is no helium-3 in the dilute liquid. So we can have this relationship. The magnetic interactions between helium-3 atoms cause the binding energy of the helium-3 atom to rise as more helium-3 atoms are added to the dilute liquid. So chemical potential mu3d0 means chemical potential of the helium-3 atoms mixed into the dilute liquid at the moment of no helium-3 liquid in dilute liquid. But if we have more helium-3 atoms in dilute liquid, then the interaction between helium-3 atoms increases. So binding energy of the helium-3 atoms in the dilute liquid become larger, so increases. Okay. Thus the relationship, the binding energy for a certain amount of helium-3 in the dilute liquid is larger than the binding energy with no helium-3 in the dilute liquid. So this relationship holds. Okay. Since the helium-3 atom is a fermion, the Pauli exclusion principle must be satisfied during the mixing of helium-3 atoms into the dilute liquid. Since only one helium-3 atom can occupy an energy level, the higher energy level should be occupied by helium-3 atoms as their number increases in the dilute liquid. The Fermi energy is the highest energy level that a helium-3 atom may occupy. As a result, we have this relationship. Since the chemical potentials of the helium-3 atom and the concentrated and the diluted liquids are equal, the relationship is given by this equation, where KBT is given by this relationship with the mu is the average volume occupied by helium-3 atoms. So we use this relationship here and this relationship here, then we can get this relationship. In the concentrated liquid, the helium-3 atom has a chemical potential of about 2.5 Kelvin. The chemical potential for the helium-3 atom in the diluted liquid is given as this relationship. Okay. We obtain the relationship of this equation if we apply the condition that the helium-3 atom's chemical potential in both liquids is the same. So we use this relationship. The amount of helium-3 that can be added to the dilute liquid is therefore 0.063, about around 6% according to this relationship. So is 3C, that is 2.5 Kelvin, and that is the binding energy of helium-3 atom in concentrated liquid, that is around 2.5 Kelvin, and this is the chemical potential of the helium-3 in diluted liquid, and we assume that the chemical potential of helium-3 atom in concentrated liquid and diluted liquid are the same. So if we equate these two equations and to find out the point of two equation meets at this point, that corresponds to the concentration of the helium-3 in the diluted liquid, that is about 6.3%. And binding energy of helium-3 in the diluted liquid is decreasing as the helium-3 contents increases, because the interaction between the helium-3 in the large number of helium-3 atoms increases, so the binding energy is negatively increasing. So E3dx has this kind of show this kind of behavior. So this one, and KBTF is given. KBTF is given by this equation. This shows that KBTF proportional to x to a third. So let's combine these two terms, then we have this curve, and E3C, and this curve will miss at this point, that is x equal to 0.063. 63. So that means that the helium-3 content in the dilute liquid at absolute zero is around 6.3%. Okay. Figure below depicts the dilute refrigeration process conceptually. The mixing chamber is where the mixed liquid is kept. That's mixing chamber. Two pipes are connected to the mixing chamber. So we have one pipe and two pipes. One pipe runs all the way to the mixing chamber's bottom. So this the vacuum pump, which is at room temperature, is attached to this pipe. So this pump is connected to this pipe. The top of the mixing chambers is connected to another pipe, this pipe, not all the way through the bottom. This pipe is used to recycle helium-3 atoms that have evaporated. So through this pipe, evaporated gases, helium-3 gas, is put into mixing chamber again. Phase separation occurs in the mixing chamber when the temperature of the mixing chamber is decreased below 0.83 Kelvin by pumping the steel. This casting can call steel. The temperature at the steel is around 0.7 Kelvin. The evaporation of helium-3 atoms into the dilute liquid is continued by a continuous pumping. And the temperature of mixing chamber reaches its lowest temperature. Okay. The helium-3 atoms are evaporated into the helium-3 helium-4 mixture by pumping vacuum pump connected to the mixing chamber's bottom, which lowers the mixing chamber's temperature. So this pipe connected all the way to the bottom, and if we pump using this vacuum pump, the helium-3 atoms is evaporated into the dilute liquid, and when these helium-3 atoms are evaporated, this evaporating helium-3 atom extract the heat from surroundings. The temperature of mixing chamber is lowered. Through the heat exchange, the cold liquid helium-3 that has evaporated, this is cold liquid, reduce temperature of the hot liquid, this hot liquid from the room temperature. So heat is exchanged. So the cooling power of this cold liquid cooled the helium-3 liquid from the pump, and the temperature of this incoming helium-3 liquid should be close to the temperature mixing chamber or using the heat exchange. The function of heat exchange will be discussed later. And we also discussed the function of steel in the later slide.